recording.
There's not.
Okay. Should I say something? Okay, good, good, thank you. So here's a couple things you need to think about, though. It's not a substitute for good design practice, okay? So any high-speed signaling you have on your board, you need to ask yourself, you know, the following questions, you know. Does the design have good power integrity? That should always be the first thing you look at on a board design. Do I have good power integrity? The second thing I should look at, are all my switch mode power supplies? Do I have my routing of the switch loop as small, as tight as it possibly can be? You know, does the design have good signal integrity? When I switch layers of a high-speed signal, am I putting a via to get the ground currents to follow that so that I don't have a big loop in the ground return for those signals? And have I also settable in the IC, microcontroller, whatever, is the drive strengths. So I need enough drive strengths to achieve signal integrity, but I don't need to overdrive the signal, right? So those are all questions you need to ask yourself at the layout and design level before you look into using spread spectrum, because those can give you more like 40 or 50 dB reduction, where this is only going to get you 15. So another place where it does not work well is a lower speed signal, like 20 kilohertz PWM. In my former life, I did a lot of motor control, right? And so, you know, you're switching the cable, right? Because the motor's not inside your module, and you're switching it at 20 kilohertz. 20 kilohertz is too low a frequency to modulate and get any results. And we'll see why later, but it has to do with the res bandwidth of your measurement versus the frequency deviation that you can actually put on a signal. Clearly, a 20 kilohertz signal can't have more than 20 kilohertz of deviation, right? So some signals that you can't apply it to. So most asynchronous communication, like CAN bus, absolutely cannot tolerate the jitter. In fact, most of you, if you actually design microcontroller-based product that has CAN bus in it, you know that typically you use a divisor of the crystal directly to reduce the amount of phase noise and jitter that you have in your CAN clock. So that's a perfect example. I'm sure the same would be true to automotive Ethernet. I don't have enough experience myself in designing automotive Ethernet to say for sure, but I have a feeling that would also be true there too. If the clock frequency or the harmonic is really close to your to a frequency of interest, say for example, we're working on a product right now that has a video clock at 54 megahertz, right? 54.5 or something like that. So the second harmonic is at 109 megahertz. So we're outside of the FM band, but if I start spreading that spectrum, what's going to happen? I'm going to leak into the top of the band. So that's, in my opinion, one of the ways to deal with some of the worst EMC issues that you have, which are quite often not non-compliance, but I've worked on a lot of product in my life where you have a receiver on the same board with your high frequency digital signals. So, you know, culprit and victim are on the same PCB. In that case, the best way to do it, if possible, is to simply move the spur out of the receiver band, right? If possible. So those are all tips and hints of where other methodologies you might want to work with. And as I stated before, you definitely want to tell your software folks that you'd like 2 versions of the code or a switch somehow in the code where you send a command so you can enable spread spectrum when you're doing your EMC work and disable it when they're doing their signal integrity work. And we'll get into why when we get to the live demo. You'll see it's pretty apparent why you want that to be true. So here, apologize to the Brody Schwartz folks. Our signal integrity scopes aren't made by Brody Schwartz. Eric, you just need to do a better job. But here's an example of an SDIO clock that some of my colleagues and I worked on. And the issue was that this was very poorly routed on one of the early versions of the board. And so we were trying to reduce it. And here is a picture of the blue or purple trace is the modulation, frequency modulation. And you can see that it's roughly triangular. There's a lot of jitter because this is coming out of a PLL inside in this case, an SOC. It's generating a 200 megahertz SDIO clock. But that's kind of what it looks like from that perspective. And so here's the meat of what it can do for you. In automotive, most, not all, of our customer specs are looking at most bands with a 9 megahertz or 9 kilohertz, excuse me, 9 kilohertz res bandwidth for their most sensitive requirements. And you can see that we're getting about 17 dB of reduction here in the fundamental at 200 megahertz. But, and here's the trick, when you start using a broader res bandwidth, you don't get nearly as large of a reduction. So at 120 kilohertz res bandwidth, we're lucky to get 10 dB of reduction. Usually it's more like 5. And then just so we really understand what the signal is doing, if I open that res bandwidth up to 1 megahertz with a 2 megahertz modulation, you can see there's no reduction at all. So again, is it a trick? Is it a real thing? It's a real thing depending on what the receiver is actually sensitive to, right? Quite often when we measure the FM band, we use a 9 kilohertz res bandwidth. And the reason for that is because we simply can't get the sensitivity that we want for the measurement. The noise floor is too high with 120 kilohertz res bandwidth. But the truth of the matter is that the front end filter of an FM receiver is 120 kilohertz bandwidth. So with that, I think, thank you for your attention, and we're going to try to make sure it works and go to the live demo. This works. Yeah, we had it working a minute ago. So there we are. There we are. Okay, so on the top is time domain, and this is coming straight out of a signal generator, by the way, folks. So I can adjust all kinds of things that normally when you turn this on in an actual IC for clocking, you don't have these knobs. There's a preset, the modulation frequency is a preset. the deviation is usually already preset. There's only one selection. So just a little caveat. I can show you live. So the first thing I wanted to point out, and I can't really use a cursor, so it won't show up in the video. But if you look out here, about here is where the 8th bit would be if this was actually clocking data, right? So imagine trying to look at an odd pattern for this, for signal integrity. It would be a disaster, right? I'd lose all of my resolution just to that, right? Without any of the jitter that's normally there in the actual data clocking. So, now we're going to play with the res bandwidth, and you'll see, right? So right now we're at 9, and I'm going to go to 120 kilohertz, and you can see how much I lost, right? Whatever form, right? And this actually gives us a better picture of what's happening in signal integrity. And I think that's because there's less computing going on at that res bandwidth of the scope. If the scope wasn't trying to generate all this and we were looking at all this on the test receiver, I think we'd see it a little differently. So, and then I can make that last change. Here again, and make this megahertz. And you can see no reduction. I'm going to go back and we're going to look at some other effects. So if I go back to 120. Hertz. Okay. And now, if I play with the modulation frequency here, you can see I'm reducing. I just went over 120 kilohertz for the modulation frequency. I was using 40 kilohertz. And you can see that it is lowering the top of the lobes. So typically this is not a knob you have. This is not a register setting you have. But if anybody in the room here is related to actually designing the digital ICs, that may be something you want to be aware of, right? So, and the other thing I can do here that you probably can't do on an IC is...
So sorry, what are you changing now?
I was changing the modulation wave frequency of the modulation. The triangle wave that's modulating the frequency, I was changing its frequency. I just went up to 180 kilohertz instead of 40 kilohertz. 40 kilohertz seems to be kind of typical, and it seems to give us optimal results when we're using a 9 kilohertz res bandwidth.
In other words, what's happening is that you're changing how fast we go back and forward.
Right. There's kind of two settings, right? There's how much total frequency deviation I have, which right now is set to 2 megahertz.
That would be the amplitude of never mind.
Yeah, it could, in theory, it would be an amplitude. That's really not the way the instruments work. The instrument is always looking for a 1 volt peak to peak input. You give it more than that and it screws it up and you see some really crazy things. But yeah, in a sense, right. So the maximum frequency deviation right now is set to 2 megahertz. I can always set that wider, right? If I, in fact, I'm looking for how I do that modulation. That's not the right button. That just turns it off. Wait a minute. modulation. Frequency. Knew where all this was. Frequency modulation. There we go. So now if I want to change this to a greater deviation, right, that will have an effect as well. Again, that's probably not a knob you have inside the IC unless you're at the point where you're still designing the silicon. But to understand the effects. One other effect that you may or may not have noticed, but when I increase the modulation frequency, the lobes become wider, right? And that's a concern, right? At some point, I get the lobes so wide that I'm pushing into a band of interest or a band that I'm more concerned about, the FM band, somewhere in global positioning system of some kind, right? I think there are 3 international standards that we usually have to meet, and they're all around what is it, Kyle, like 1.5 gigahertz or something like that. But the free, it's like 5 decimal places. It's very exact what frequency. And quite often they use even lower res bandwidth there, like 1 kilohertz, because they're trying to capture really low noise floor. So, but you can see, now you can see what I really did to signal integrity. What a disaster, right? So,
you mentioned disabling spread spectrum for signal integrity, right? To analyze it. So that's only to optimize the circuit, but once you turn on spread spectrum for the product,
yeah. And typically, but again, signal integrity work is done. You prove out the board and the silicon.
Without
In theory, we do this before DV. Though my colleagues are chuckling because that never happens. But in theory, that's what you'd like to do. First we get the layout straight, both for signal integrity, power integrity, and that helps us to optimize for EMC as well, right? Then we try and get the settings on the drive strengths and whether we're going to turn on spread spectrum or not, get those things all set right? One of the things about having a good layout for signal integrity is then I can reduce the drive strength. It's much harder to drive a line that's imbalanced, that's an improper impedance and has way too much return loss in it, right? So I have to drive it harder. So it's a sort of a double whammy, if you will. So where am I at time-wise? Oh, I lost it. Oh, yes. So, yeah.
Question like a lot of IC they don't offer like spread spectrum.
Yes.
Is there any way that we can integrate in like hardware?
Not that I mean, in theory, yes. In theory, most ICs I can pipe the clock in from the outside. But if you consider that I'm going to create the clock now on the outside, and now I'm going to route that clock instead of having it routed inside the IC, now I have to route it on the board. It's probably not going to help me, but in theory, yes, you could. In theory, yes, you could. And to be honest with you, I'm not enough knowledgeable on how to design the silicon of that PLL to know the details of what they're doing. Whether they're just introducing noise into the loop or whether they're actually modulating the reference. I really don't know. Another thing you need to be aware of too is quite often this clock signal is going to be divided, right? The PLL is going to run at a very high frequency, usually 200 megahertz, 400 megahertz. I think there probably are some systems out there now, some chips, single chips that are out there that are running almost a gigahertz at the PLL. But then you divide that down for various clocks. So as you divide it down, you're going to have an effect. I was hoping to get a board put together with a counter on it and a divider, and I didn't, so I apologize for that. You're gonna lose some of the effectiveness of that, right? Which is, I think, why they modulate at a lower frequency. Because obviously, if you divide down below the modulation frequency, you'll wind up with pretty much a straight signal tone. It'll have some jitter on it, but it won't have the spread factor that you want it. So, I didn't know if there were any other questions that anybody had.
So what is the recommendation for which frequency of operation you can use the spectrum? As you said, we can go lower in the frequency.
I would. So I've seen spread spectrum used a lot of switch mode power supplies that run at say 400 or 500 kilohertz. So it can be effective, but if you get down to 20 kilohertz, it's just probably not going to be effective.
More the higher range.
Now in the higher range, I think it's effective. The thing again now is you've got to look at, am I close to a band of interest, right? If I had, say, a clock at 260 megahertz, well, if I apply spread spectrum, am I going to leak down into the DAB band, right? It's I think 247 or something is the top of the DAB band. Again, if my spur is just outside of one of the global positioning, right, or just outside of, I don't know how many requirements we have here, but I can tell you they're coming for all of the bands that are going to be part of, 6G, right, and even 5G bands, as well as your higher end of the Wi-Fi bands. Right now, we're not measuring those, or we don't have requirements there for a lot of our OEMs, but they're getting ready to implement them because those are going to be the frequencies of interest. Sadly, a lot of our OEMs are looking at taking AM and possibly even FM out of their cars. And that's related to the emissions of electrification, right? It's pretty hard to run, a half or a quarter of a megawatt inverter, and not produce anything in the AM band. That's really difficult. And for those bands, so there are some other tricks that you need to be aware of. One of the classics, and it was patented, but it's now public domain, is what they call radio frequency method. So I can dither my 20 kilohertz by just a very tiny amount and move the harmonics outside of the tuned radio frequency. So if the tuned radio frequency is on the bus in the vehicle and my module is aware of what it is, all I do is move my frequency just a little bit, right? That's one of the best methodologies because there's no extra energy involved in that. If I have a high power 20 kilohertz signal and I try and change the slope control, now I'm dissipating more power, right? The longer the slope, the more power I'm dissipating. And unlike driving a high frequency clock line where that power is not such a significant factor, it's a big deal if I'm driving on a 20 amp motor at 12 volts.
So if I have a broadband noise in AM band, so the method that you mentioned, RF method, will that help?
Probably not, because broadband noise has got a different, especially down in that lower frequency, it usually has a different source than period. In general, broadband noise is not coming from a periodic signal; it's coming from something incoherent.
So, for an example, let's say we are driving a motor for 20 kilohertz. So all the harmonics in AM band, it's not significantly different between, let's say, I think first one is 530 kilohertz, then it goes till 1.73. There is multiple
there'll be a lot of spurs there, but again, if I know which one of those frequencies the receiver is tuned to, the vehicle receiver is tuned to, okay, and this is a standard method. All of the OEMs have done this for one or another kind of control. Okay,
Is it like kind of from like circuit level, or is it like they're changing in like AM?
so what they, no, yeah, no, it's at a system level in the vehicle. So what happens is you tune your receiver, the receiver puts a message on the CAN bus or whatever bus you're using to communicate globally within the vehicle, says, I'm tuned to, you know, to 620, right? So then whatever it is that PWMs gets that information, and they have a lookup table that says, okay, instead of PWMing exactly 20 kilohertz, I want to PWM at 19.87. Okay. And so then that puts the two spurs on either side of the receiver. So again, that wasn't my original topic. That's actually one of my greatest experience or longest term experience with working on emissions issues, because I was a lead for that type of product for many years. So that answers that question, and we can go over that topic in greater detail. Again, that's one of the hardest things as a hardware engineer. A lot of these solutions you're leaning on software for. So cultivate those relationships, difficult as they may be, you know, that'll help you, I believe, a lot. But again, be aware of where it helps you and where it doesn't help you, and look at all the effects, right? So it might be perfectly fine to spread spectrum at the fundamental, but what about the third harmonic, right? Or the fifth? There's typically clocks, most CPU clocks are symmetric waveforms, so I usually kind of only have to worry about the odd harmonics. Of course, until I get up there to like, you know, the 50th or 60th harmonic, at which point the signal's not that perfectly symmetric, so I get all of the harmonics, not just the odds, or not just the evens. So, any other questions? Yes.
New standards, you're going to network teams. How does that? I think there are quantified resolution standards, right? Will the FFT
Well, actually, they do. They do. That's part of the mathematics that's inside of that digital receiver IC, right? That is those kind of products. The receiver side of those kind of products is also a big part of the products that my company works on these days. And yeah, you know, because if you didn't have that kind of filtering, whether it was digital or analog, you wouldn't have the sensitivity of the receiver that you need, right? So that's part of the routines that they're doing. It's just they're doing digital filters instead of doing analog filters. The effects are the same, more or less, right? There are a few things that are different, but no. I think I pretty well used up my time, unless there's another question. Any more questions? Thank you. Of course. Now, someone has to try and get all the same beat stuff. so-
Yeah. That'll take 15 more minutes.
That's perfect.
Stuff you don't hurt him.
Here.